So this is going to be a little bit of a whistle-stop tour. I understand, given the time zones, most of the audience might be a little Europe-focused, but I hope that getting a little bit of perspective from different parts of the world and bringing a voice down from the Indo-Pacific, you might see some different things here. So we're going to be talking about geomechanics in what I call conventional resource development. We're going to start with a few definitions. We're going to run this whole thing based on questions, to consider motivation. What motivates us to use geomechanics in conventional geothermal? Going to look at our context, some applications, some examples, and then finish up with some next steps. So what are we talking about when we talk about geothermal? So there's different kinds of geothermal resources. It's basically any kind of heat we're utilizing or extracting from the earth, and it goes all the way from shallow geothermal heat pumps somebody might have on their house, hot sedimentary aquifers, of which there's some great examples like the Paris Basin, hot dry rock, EGS, and I now call it EGS++. There's a lot of new innovative technologies to sort of look for that heat anywhere solution. And then there's two others. There's a deep circulation geothermal systems and volcanic geothermal systems. And these last two are what I'd refer to as being conventional geothermal systems. They're fluid that's naturally heated and convecting through existing crustal permeability. We're not generating permeability, although we do stimulate wells in some cases to improve, but the permeability in the system itself is already there. The reservoir, which is the developable part, is typically more than 120 degrees. You've got resources up to about 330, 340, some of the volcanic systems like Puna. And they're not closed, they're dynamic. So they have fluid upflowing into them and outflowing or discharging out of them. And so they can either be hot water, single phase, or above 220 degrees Celsius, they're two-phase, steam dominant or liquid dominant. And so in terms of extraction, we're either pumping these wells if they're cool, or they're self-flowing through the energy of boiling. And rarely they're artesian, there are a few cases around. And so they're utilized for electricity generation, primarily direct heat and clean steam. And so when we're thinking of these conventional geothermal systems, I'm going to see if I can get a pointer that is a laser. Here we go. We can think of like a whole regional system where fluid's moving through the crust, but then is being localized and focused into a thermal anomaly, fluxing up through the crust, hitting some kind of cap structure, typically a clay cap, and being deflected to form this wider reservoir unit. So the reservoir unit around this double eight here is an upflow and an outflow, one or more discharge zones. And typically when conventional geothermal people are communicating with each other about the reservoir, about permeability, we're often using isotherms, so lines of equal temperature, because it's that movement of fluid that's generating the thermal anomaly. So there's around 200 developed conventional systems in terms of developed for energy, electricity usage. There's also on the sides of many of these direct heat, clean steam, industrial areas, etc. And you'll notice that they're mostly on plate boundaries, eastern US with a little bit of excess heat flow through the basin and range, but they're really sort of like those hot places in terms of heat flow on our planet, but also co-locating the structure. And when you seek to explore and then develop systems like this, you've got three key elements of risk that you're trying to manage. So one is geochemistry. You want it to be benign or manageable. And so what that means is you don't want to be developing an acid volcanic system, or you need to generate the technology in order to manage that sort of issue. There needs to be sufficient temperature for that planned development, whether you're lower temperatures with pumping fluids or higher temperatures. So whatever you're doing, you're matching to the development. And then enough permeability for sustained well flow over the desired time frame, which tends to be a project lifetime plus. Many geothermal systems, like the oldest wet steam field development of the world, Wadaki, they've produced like a couple of times the volume of the actual reservoir. So because these are dynamic systems, upflows, outflows, if you've got the permeability and you're managing the resource well through injection, you can get these really quite substantial project lifetimes. But of these risks that we're identifying and managing as we go through the resource assessment, the most difficult one to get a control on is permeability, and that's where geomechanics contributes. And so what are we talking about in terms of permeability for geothermal systems? You can get a geothermal anomaly, so a thermal anomaly, geothermal system occurring sort of at 10 to minus 15 meters. But in order to get wells to flow, you need permeability a couple of orders of magnitude higher than that. So you're talking about that real fault zone permeability to generate these flow zones. It's tremendous flows. Like for the reservoir engineers who might be in the room, like a standard geothermal well is often flowing 20 to 50 tons per hour. And I understand that's a couple of orders of magnitude, even taking into account things like friction, higher than a typical oil well. So system type dictates in many ways the utility of geomechanics. And so we have to consider what kind of system we're in, but also how the permeability is functioning inside those systems. And so we talked about volcanic geothermal systems or these deep circulation geothermal systems. So volcanic, we tend to classify based generally on settings. So we've got these higher elevation andesitic arcs, or we have magmatic rifts that are either mature basaltic dominant, so somewhere like Iceland, or the adolescent rifts like New Zealand's Taupo volcanic zone, where we have like this thicker silicic pile, a thicker crust situation. Over in deep circulation systems, you're either looking at waning volcanic centers, which are a little bit less common, or extensional provinces with elevated heat flow, like the Western US Basin Range province. And in those cases, faults play a tremendous role in how fluid's getting around and up to the near surface where it can be developed. So we can talk about this thermal anomaly, this reservoir, on a spectrum, and from a very distributed system on the far right-hand side here to something that's much more focused around geologic features like faults or some sort of horizontal layer with high permeability. And essentially it's the degree to which the fluid flux will cross-cut the geologic features. And that cross-cutting is a function of permeability contrast. So theoretically, the background permeability in this case B, where the geothermal system is focused very around this fault and this tabular outflow, the background permeability could be sufficient for convection to form, but because of the permeability contrast between the fault zone and the area around it, you end up with this localization of the thermal anomaly. In practice, often actually away from these fault zones, it is lower permeability. So you get these quite steep transitions from drilling a well that's productive to drilling a well that's not productive. And that's wherein the problem lies. Whereas right out at the other end of the spectrum, like if you have a very distributed permeability system, you can drill wells and not get that like same contrast in results. And historically, we've developed more either at this end, this distributed end, or the sort of shallow, easier to target horizontal portions of the sort of more focused systems, and the larger systems as well that were clear from the surface using thermal manifestations. It's really only been the last decade that the frontier is pushing into more difficult to develop systems, blind geothermal systems, so no surface manifestations, and systems where you're drilling adjacent wells quite close together, sort of like even one leg in a sidetrack, with extraordinarily different permeability results. And so that's where geomechanics is coming in and contributing. So what we're going to be working through today is a workflow that I've developed from actual practice of what's going on inside successful geothermal development companies, of how they go through the resource analysis process, so the subsurface characterization, focusing primarily on this risk element of determining the extent and controls on permeability. And so that's thinking about where are your reservoir sweet spots, so like where would you be targeting wells, fluid flux pathways, so what's the connectivity between the reservoir, because we're not talking about something static that we're extracting from, we're talking about a system of connections from an upflow through to an outflow. And then as you're going through development, you know, you're going to have injection wells and production wells. So what are those fluid flux pathways and connections between those? And inside that, we're having to consider both the structure and the influence of rock properties on that extent of permeability. And we take these results and we apply them to something that we call the conceptual model. It's a key tool in geothermal that is a systematic description of the resource and all the different technical elements of the subsurface. We use it for well targeting, development plans, as well as reservoir management. So historically, typically, you know, like we'd our key inputs would be through the structural and geologic model, which generates that sort of spatial three-dimensional framework. And then that interdisciplinary integration, you know, geothermal resource teams work in a very close interdisciplinary way between reservoir engineering, geology, geochemistry, and geophysics, all to sort of come together around these problems. And geomechanical modeling in these more complex systems or complexly permeable systems is the piece that is contributing to the story. You know, like it's not the panacea. You're still integrating all of the other parts together, but it's contributing to the analysis. Right. So the upper part of the figure here is the typical elements of the geologic parts of the workflow. And a lot of this is familiar. You know, we may have some borehole images determining structural features. We may have other kinds of geophysics, field surveys, etc. We may have cuttings and core analysis. Petrophysics is very rare, not commonly done. Some people use also drilling parameters. And we're essentially trying to constrain in 3 dimensions faults, fractures, but as well as that, the alteration history, because the hydrothermal alteration really does influence the permeability, rock mechanical properties of the system. But there's this sort of range of geomechanical elements that we can then plug into the system. And so that's going to be the focus of this talk. But while we're going to be talking about these geomechanical elements, piece by piece, they also integrate closely with the classic geologic elements. So you need to sort of have a close integration with the structural model, with the what's going on with the petrography. And that's why any projects I've done has been in close collaboration with the internal resource team, because they are the holders and the people who really understand these elements of the geothermal resource. So we're going to start with input data. So borehole images are run in high temperature geothermal wells under injection. So you're basically injecting into the well and down to the point where your cooling fluid leaves the well, which tends to be the deepest major permeability. You can run standard temperature tools in wells that are, when re-equilibrated, you know, sort of 240, 270, 300 degrees Celsius. And what we commonly find is there's this really complex relationship between the lithology and what we're seeing in terms of the fracturing. And we also see, you know, like on the left-hand side is a microresistivity image. This is a feed zone, it's a flow zone. And we do see really massive fractures in the subsurface. It's 1.6 kilometers deep. And the width of the fractures, we see it on the image here, plus or minus some spalling, you know, like a sort of upwards of 10 centimeters in places. So we really do see some really large fractures in the subsurface. What we also do see is alterations. So on the right-hand side, we see haloing, bright haloing around fractures that are most likely pyritized, so attracting current from the tool. So all of these things need to be unpicked when you're dealing with this primary data. What also needs to be unpicked is the fact that we're dealing with very hot wells. And when you take drilling fluids, downhole, maybe 50, 60 degrees Celsius by the time you've circulated down the drill pipe, and you're running it into a well that's sort of 200, 300 degrees Celsius, you're thermally cooling the borehole wall. And that really influences both how some of our fractures appear at the borehole wall, but very much how our stress features appear. And it's those stress features that we're using in the geomechanical modeling. And so what we find is borehole breakout is extremely rare unless we have quite soft rock, or we have very strike slip conditions. And instead we have really, really intense drilling-induced tensile fractures. So if you look at the image on the right, what you're seeing is these sort of like very clear, gaping, almost fishhook-like tensile fractures that are interacting with features on the borehole wall, where the lower part of this image is a dike that's intruding into a volcanoclastic breccia. And so essentially, these sinusoids, these curves, is the amount of stress felt, the hoop stress felt, if you unwrap the borehole. And then if you had a well that was like not hot, you'd be this top curve here, and you'd form borehole breakout where you breach the compressive rock strength. And as you heat up your reservoir, your thermal stress is essentially a subtractor, and you end up with increasingly tensile conditions. Like you never actually reach these conditions because what you have is tensile failure that's in tensile conditions around quite a large amount of the borehole wall. Another kind of input data is measuring the magnitude of your minimum stress. And in geothermal, this is very historically really done, and often poorly done. What we find is in our hard rock environments, there's often very little correspondence between a leak-off point and the actual sort of fracture propagation pressure or instantaneous shut-in pressure that would more confidently constrain the minimum stresses. And so you actually need to do complete cycle tests in order to be able to determine the minimum stress. What we can do, though, is in conventional geothermal systems, we find them in normal strike slip settings. Often they're transitional. Yeah, I don't think there's any in the world that would be in a compressive setting. And we can assume a critically stressed crust and use a Coulomb frictional failure equation just for normal folding, just as a minimum bound, as like sort of a reasonable assumption. What's much better is if we plan ahead and conduct a few of these extended leak-off tests to give some constraint. So once you have some foundation data, you can go on ahead and construct a geomechanical model, which is essentially a definition of the principal stresses and the pore pressure. So the principal, and I found there's a lot of standard approaches, straight technology transfer from what's been developed for oil and gas resources. But there are a few exceptions, like when you're working in geothermal systems. And a great example is how you would constrain the pore pressure gradient. And so on the left-hand side here, the little green dots each represent a well. And there is one point on a well pressure profile that actually relates to the reservoir profile, the reservoir pressure, and that's called the pressure control point, because as the well is cooled or heated, the pressure profile inside the well pivots around that point. And when you have multiple wells, you can then interpolate what the reservoir pressure is from this. And so in this case, we have a deep reservoir. Then we also have a cold, shallow aquifer and a hot, shallow aquifer. And the blue curves on this represents a standard hydrostatic gradient for a 25 degrees C crust, so global average. And so you'll find that these geothermal systems are hot hydrostatic, so under pressured relative to the discharge zone. And then you start getting this additional complexity. So there's like quite a big figure on the right-hand side here, but I want you to focus in on the top right-hand corner, where R is the reservoir pressure gradient. And so we've got this liquid pressure gradient, and at this dashed line point here, we hit the vapor-dominated zone. And in the vapor-dominated zone, the pressure is near isobaric till you get to the base of the clay cap. And when you go back through sort of a gradient that connects up to whatever the shallow groundwater gradient is. And so reconstructing that pressure gradient is very different to how you do it in oil and gas. And so, you know, while we can straight up technology transfer between the two, we need to really consider the reservoir physics and data availability. And so regarding that data availability point, in geothermal systems, we tend not to run petrophysics through these clay caps due to collapse risks. So we're a little bit more limited in terms of interpolating the overburden. So once you've got a geomechanical model, you can do some static fault and fracture modeling. And so what that is where you take a modeled stress state, so that tectonic stresses plus pore pressure, and you calculate the likelihood of slip, where slip tendency is defined by, you know, this ratio of shear stress to normal stress. So whether or not the probability you'll get the slip, and dilation is kind of like a forced closing on the fracture or not. And if you add these two together, you end up with a hybrid tendency. So essentially, like where fractures are most likely to both fail and generate open space. And so there's a nice fracture, it's always a nice fracture. There's no paper by Farrell and others that describes this process based on outcrop observations, where you see on the sail plot, we've plotted this most favorable zone here, and that's whether you get this hybrid failure, where you've got some dilation, or on the shear failure, if the asperities or the roughness on the surface of the fractures or mineralization in it is enough to sort of self-prop, then you get sustained open fractures. I'm finding slip tendency alone is not always diagnostic of what our feed zones are. So our feed zones are places where fluid is flowing into or out of the well, noting that geothermal wells are either, there are many that are barefoot pleated, but you just basically drill your production section and then you squat a pre-perforated liner in the well and then you test it. So there's no way to determine where your flow zones are going to be. So there's no cemented liner with perfs, it's just a pre-perforated liner. But irrespective of not being able to, it being fully diagnostic of the feed zones, we can understand things about the fractures themselves. And so here we have just a frequency count by depth of the fractures in this well. And at the bottom, it looks like there's many, many, many more fractures than there is in the rest of the well. But when you calculate a slip tendency, you'll notice that things even out a little bit, and this zone up here seems to be more important. What we're often finding is where you get these localized peaks in fracture frequency that's shaped like this, there tends to be around larger fault zones, and often large permeability tends to be around larger fault zones. And so what's happening is this bottom unit here is actually an andesite, and what we're seeing is thermal parting likely on flow banding as well as jointing in the andesite that's not related to connected fractures. We also might combine with other fractures. So we often see in geothermal wells localized stress rotations, and commonly localized stress rotations are associated with flow zones. And then more recent work, we're combining slip tendency and dilation tendency and finding it more diagnostic. But you'll have to wait to the World Geothermal Congress next year for us to publish that one out. And then finally, rock mechanical properties really influence how fractures occur, and we will have a look at that in a later slide. The next thing I want to touch on is this concept of dynamic fault modeling. And so we're going to step up in scale, noting that the static modeling could be done either at the wellbore scale, like the example that we've talked about, or it could also be done at the reservoir, or it can be done at a larger fault scale. But this dynamic fault modeling, essentially, we're looking to take a fault model and a stress state, and through many fault cycles over time, simulate the slip on those faults, given that stress state and the incremental changes in that stress state, to find the changes in stress and strain as a result of that fault slip. And so this is work a collaborator of mine has been pioneering with Drew Seiler, Geologica Geothermal Group. And he's demonstrated it using this set of empirically defined structural settings. So this is the work of Hines and Folds and others. It's been well recognized in other geologic settings, but this is out of the basin and range, where we're relative to, we're looking at a plan view of fault patterns and where the geothermal systems are localizing. So you're seeing them localizing in these complex interaction zones. And so Drew's modeling has shown that the fault complexity inside those inside those fault interaction zones are focusing the stress and the strain, which is promoting the permeability. So herein lies your sweet spot analysis when you're looking at the reservoir scale, but it's not equally so. So you've got shear stress change, and so where the high values indicate the probability for slip. We've got this dilation change where higher values indicate the probability of dilation. So again, red values here. And then you've got this normal stress change. You can think of as like lower values, pink here, is unclamping on these faults and fractures. And there's pretty close correspondence between these modeling results and where empirically through field observation and wells and thermal manifestations, springs and so forth, where the geothermal systems are actually localizing. But this modeling is particularly sensitive to whatever your structural hypothesis is and the geomechanical model. So this is an example over here. Oh, sound? No? Right.
Yeah, 5 minutes.
Perfect. So it's an example over here where they've got a slightly different stress azimuth and a different fault model to try and explain the same thermal manifestation area. And you end up with a very different zone of favorability if you change those parameters. So to be predictive, you need a reliable geomechanical model and a robust structural model. Or you can go back the other way, which we've recently been testing, where given you know things about the permeability, in particular like a well-drilled field, thermal manifestations, you can use this to go back and test structural models and then infer beyond your currently drilled area. Finally, mechanical stratigraphy. And so when I say mechanical stratigraphy, I use it as like a catch-all term for what is the rock properties, the distribution of porosity, the rock strength, and the tendency of like self-propping brittle failure. And so mechanical rock properties influence the likelihood that we'll have sustained open fractures from slip. Essentially on the right hand side here we have a nice figure from one of my ex-students who's leading the way in Indonesia in geomechanics study right now. They're dealing with systems over there with highly variable rock properties, and so what you have here is a lava unit in amongst a tuff, and most of the fractures, including the ones that appear open at the wellbore wall, are localizing inside the lava units rather than inside the tuffs. Hydrothermal alteration has a massive impact on mechanical rock properties. If you have like smectite clay alteration, you can imagine that rupture through that is more likely to reduce permeability than it is to create it. And so I really advocate taking our time-based geologic stratigraphies and reformulating them into sequences of rock properties, particularly simplified sequences of rock properties, so we can use them to look at our geomechanical model results, but also they're really good for geothermal numerical models, numerical reservoir models, where we look at processes of heat and mass transfer. So when you put this all together as a workflow, we're really targeting on this. What is the extent and controls on permeability? But we have to approach it from a multidisciplinary way. So the classic geologic integrating geomechanics and then integrating with reservoir engineering, geochemistry. We have to approach it multi-scale, from the wellbore scale, often more static studies, to this reservoir scale dynamic studies. And then in geothermal, particularly because there's so few systems developed in the world, like we often end up having to rely on analogous reasoning. And so both finding analogous outcrops as examples to look, because we tend to have very poor core return, poor core recovery because of our fractured systems, but also looking at analogous geothermal systems that are much more well drilled for information on what could be going on. So where are we going with this? So geomechanical modeling, because of this history of developing very large distributed systems that often cross-cut the geology, and only more recently in the last decade or so, developing much more complex geothermal systems with much more difficult constrained permeability, it's really in its infancy. And I'm certainly not arguing that it's some kind of panacea that'll solve all issues. But inside this resource evaluation framework, particularly for these more complex structural resources, whether it be like a multi-fault controlled system in the mega shear zone in Sumatra, or a deep circulation fault hosted system in the Western US, the value of geomechanical modeling suddenly increases. But we have to match the methods to the target problems and settings with reliable data input, and consider the uncertainties. Like we often don't have the luxury of some of the data that is acquired on the oil and gas side in geothermal, just because the conditions are much more difficult to work in. And then we have to fully incorporate any results back into that resource evaluation workflow. Like put it back into the conceptual model uncertainty, really consider it against all of the reservoir engineering data, be it numerical pressure transient evaluation or interference testing, reservoir tracer testing. There's so many ways we can approach our understanding of permeability, and it's about putting all those parts together. Finally, I really advocate for support from industry for open publication, because there's so few of these studies happening. I know a lot happening commercially, that in order to build as a group, we need to sort of be daylighting these. And so on that note, most of the cited literature in this presentation you can find through the International Geothermal Association conference database. You can download a high resolution version of this workflow from Figshare. Just Google Figshare and the name of the workflow, Structural Geology and Geomechanics Workflow for Geothermal. And as John said at the start, I open source my code, as does my collaborator, Drew Seiler. His dynamic slip tendency modeling, his dynamic fault modeling code is downloadable through the USGS. And I think I might be right on time.
That's
Do you have any questions?
Excellent timing, Irene, and fantastic presentation. And we already have some questions in the question panel. I have not assigned them yet to you, but I can just read them out to you. The first, hi Tom, it's from Tom Bratton. What log-based permeability transforms do you find most accurate?
When I'm going to have to ask a question back to this question. I've recently in natural hydrogen work started working with folks who are working in oil and gas. I come from first a mining and then a geothermal background. And so there's a lot of assumed knowledge in oil and gas that I'm not up to speed on. And so when you say log-based permeability transforms, what do you mean? Gerald, fill me in.
I will enable Tom's mic just now. 1 second, Tom. Your mic should work, Tom.
Okay, perfect. Many times we use, porosity transforms. We transform porosity into permeability, and like water saturation equations, you can find, like 8,000 or 9,000 of them. So okay. Is there? Do you have access to logs where you can, get a handle on this important parameter based on log analysis?
So I've been working in geothermal logging. I ran the first successful runs of standard temperature rated oil and gas patch tools in geothermal wells in New Zealand about 12 or 13 years ago. And I've probably seen half a dozen porosity logs. They're not typically run. We do have a tradition of starting to run more borehole images, but they're virtually not run at all. I think one of the key issues is clay-bound water. We have a lot of clays in our system, so you'd have to do a lot of accounting for that. So when we actually think about permeability, for lower permeability systems, we tend to be looking at inflections and temperature profiles. But when we're well testing wells, we're actually looking at doing fluid velocity profiles. So things called PTS tools, pressure, temperature, and spinner. And you're doing full well tests to determine permeability. And then you're directly comparing your borehole images and your results to that reservoir engineering data with an understanding that you may have a pre-perforated liner. So things could be offset for up to 10 to 15 meters. So it's all a little bit hairy.
Thank you.
Okay, we've got another question from Nader Fardin. Could you please explain what is tilted SV?
Tilted SV. Yeah.
Tilted.
Terrible.
It is not vertical anymore? Question mark.
Great pickup. I did actually, that's papers from a few years ago. That actually should be a tilted sigma 1 in that particular case. So it's a normal stress setting. I should have overwritten that label. And we had some really nice moment tensor inversions from thermal stimulations in that well that showed that the sigma 1 was actually tilted. And so we were experimenting with using, instead of an assumption that the vertical stress in this normal setting was the largest, we were using this tilted set when we were calculating the slip and dilation tendency. So good pickup. Labels.
Okay, those are the two questions in the chat. We still have a few minutes left for questions for Irene's talk. Oh, yes, we do have another one here. Attila Petrick, I'm going to sign it as well, Irene. Great presentation. Do you also integrate acoustic logs? Thank you, Attila. I was going to actually bring up acoustic logs. Cores to have a better grip if fractures are open or closed. What methods do you use to determine fracture aperture? How do you address the problem of fracture connectivity? Have you tried using borehole images for that purpose? Thank you, Attila. Great question.
Thank you, Attila. It's the talk I love giving. Are you planted? Let's talk for another half an hour on this. So when you say acoustic logs, so there's acoustic borehole images. So where you're sending out a waveform, you get it pinging back, so you have a change in amplitude and you have a change in travel time. And so we use a lot of acoustic borehole images in geothermal, and we're often using the travel time signature to determine if things are actually open at the borehole wall. And so that's very commonly done. More companies now are running both microresistivity images and acoustic images together in order to be able to get that lithologic information from the microresistivity imager and can sort of understand some of the controls, and then combining that with the acoustic imager. In terms of full waveform sonic, it's still a little bit frontier research for geothermal. I've not seen convincing results. I know there's like a lot of work done in noise processing. There's a lot of work done to sort of forecast fractures away from the wellbore. There's a lot of work done in, you know, like looking at anisotropy. But I've seen nothing to date that's more concrete and more coherent with the rest of the resource data than the more basic technologies right now. And so I think some of the challenges is just the conditions. You know, like we have commonly boreholes that are more than twice bit diameter. You know, like we have a lot of borehole rugosity. I think it's a real challenge to acquire the kind of like high quality data that you get in gun barrel wells. And that just makes actually using a lot of these tools in geothermal wells really challenging.
I actually unmuted Attila if he has any follow up to
I
that.
didn't specifically to width and aperture, but did Attila, did you want that bit talked to as well?
I'm interested in the width and aperture as well.
Okay, all right. So we have 2 minutes. So there's an excess resistivity model, Lutfi and Sophie, what is it, 1990 or something, that's built into most software that people use to invert electrical aperture from the micro resistivity image. I've not seen it perform well in hard rock environments. It seems heavily influenced by background resistivity, and I'd certainly like to see more calibration cases and clear systematic study. When these have been done in geothermal settings, the results also haven't been coherent to what the independent reservoir engineering well testing is saying. What we do find is more coherent, however, is actually just really manually measuring width. And so all fractures, mineralized or not, has a width from top to bottom, plus or minus an alteration halo. And so there is a systematic relationship between fracture width, particularly of those that have a low probability of being mineralized, and the reservoir engineering data set, so where the flow zones are, et cetera. And so I do think there's a lot more work we could be doing on width and aperture. I have actually given another SPWLA talk on this topic. I think it's on the YouTube somewhere. But yeah, it's wide open right now. And yeah, if people have more comparative case studies where you've got both a micro-resistivity image and an acoustic image, both very good quality, I'd really like to see these cases cross-matched in different geologic settings, because then it doesn't seem to be performing well in hard rock.
I hope the pun was intended just then, Irene, actually, regarding the state of fracture aperture being wide open. Very good. So we are bang on time. I think we'll take that time advantage and continue. Thank you, Irene.